Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures on random signal theory. We are still in chapter 7, which is entitled Sampling Distributions and Parameter Estimation. Now, we are continuing with the topics of this chapter, and today we would like to talk about one of the most powerful theorems in statistics. It's called the central limit theorem. So, before we actually begin with the slide, let me show you just my own note on that to begin with. So, let me start with the context. So, what is the main context for today? We have a population, and as you know, the population contains all the values, and we know that populations can be represented by random variable. So let's say X is a random variable that represents a population, and that population has mean mu and variance sigma square. So mu is the population mean, the average of the entire population, and sigma square is the population variance. It is the variance of the entire population. In addition to this, let's begin with the assumption that our population or random variable X has a normal distribution. Let me give you an example so that you understand the context. Let's say I'm focusing on the GPAs of all university students in the world. So I have a population which contains all the GPAs of every single student in any university in the world. This is my population, so it may contain millions of GPAs. Now, having this population, we assume that we know that the mean for this population is mu, the population mean, so the average of all GPAs is mu, and the variance is sigma square, or equivalently standard deviation is sigma, so the variance is equal to sigma square. This is our population. Now, if the population is too large to deal with, or if the random variable that expresses this population is not known exactly, what are we used to in this chapter? What is the idea that we introduced at the beginning of this chapter? Is that we can take a sample at random from the population that might help us. So let's assume that x1 and x2 until xn represents a random sample that we take from the population. So if we stick to the GPA example, so our population contains all students' GPAs in the world. Now I choose a sample at random. Let's say this sample is our class. So x1 would be the GPA of the first student in the class. X2 would be the GPA of the second student in the class, and so on. Xn would be the GPA of the last student in the class. Of course, since the sample has been chosen at random, I've chosen our class at random from among so many classes I could have chosen, or from among so many samples. I could have just gone to the street and chosen a sample of 50 students at random and observed their GPAs. In that case, X1 would be the GPA of the first random student in the sample. X2 is the GPA of the second random student in the sample. Xn is the GPA of the last random student of the sample. We know from the beginning is that because the sample is chosen at random, then x1 itself is a random variable, x2 is a random variable, until xn is also a random variable. Now, these random variables here are not just any random variables. These are random variables that were basically taken from the same population. They represent observations that were chosen at random from the same population. So although x1 is random, but its average, the expected value of x1, is the same as the expected value of x2, is the same, and so on, until the expected value of xn, which is equal to mu, the population mean. Now, what was x1 again? x1 was the GPA of the first student in my sample. What is the value? Of course, it depends on the sample. And since the sample is chosen at random, on average, the value of x1 is the same as the population mean, the sample that I'm taking this observation from. So in short, x1 and x2 until xn are all random variables that are drawn, taken from the same population. That's why their expectations are all the same, which is equal to mu. Likewise, using the same argument, the variance of x1 is the same as the variance of x2 is equal to, and so on, is the same as the variance of xn, which is equal to sigma square, the same as the population variance. Again, simply because x1, x2, and so on until xn are all observations, are all random variables that are taken from the same population. So the variance is all the same, equal to sigma square, which is equal to the population variance. Now, let's define something new. Let's define x bar, which is the sample mean. X bar should represent the average of these random variables. So if x1 is the GPA of the first student in the sample, and xn is the GPA of the last student in the sample, then x bar represents the average GPA of my sample, not the average of the entire population, no, the average of my random sample. So we know from before that x bar, the sample mean, is equal to x1 plus x2 plus and so on until plus xn divided by n. So we notice, just to connect to chapter 5, because we are taking these results from chapter 5, what you see here is a linear combination. So x1 and x2 until xn are all random variables, and the expectation of each one of them is mu, and the variance of each one of them is sigma square, and then we define a linear combination which is the same as the average of these random variables. So this represents case 2 of our linear combination. So what do we know from chapter 5? We know that the expected value of this x bar is equal to mu, the same as the expected of each one of the variables. And we know that the variance of this expression x bar is equal to sigma square divided by n, and n is the size of the sample. Now, in addition, since the population from which we have taken these variables has a normal distribution, then each one of these variables has also a normal distribution. And from chapter 5, that x bar, this special linear combination, has also a normal distribution. And now that part number 3, observation number 3, represents case 3 of the linear combinations of chapter 5. Let me just show you a part of that proof, small proof, as a reminder. How can we calculate the expected value of x bar? In other words, it's the expected value of this expression, x1 plus x2 plus and so on until plus xn divided by n. So this is just a linear combination, and by applying the result of the linear combination, how can we express this expectation? So it's the constant times expected value of x1 plus constant times expected value of x2 and so on. So each one of the constants is just 1 over n, so we can take it as common. 1 over n is the common constant. And then the expected value of x1 is mu. Expected value of x2 is also mu, and so on. Expected value of xn is also mu. So in short, we have 1 over n times open bracket, and then inside the brackets we have mu, and so on until plus mu. However, how many mu's are we adding here? The same as the number of terms. So this expression is equivalent to n times mu divided by n. So the n will cancel, and the answer is mu. We have seen this in chapter 5, even using the same proof. So the expected value of that average, the expected value of x1 plus x2 plus xn divided by n, is equal to mu, and we have seen the proof. Now, how can we calculate the variance of x bar? So it is the variance of x1 plus x2 plus and so on plus xn over n. Again, how do we calculate the variance of a linear combination like this? Assuming that x1 and x2 are independent. So assuming that my sample is chosen independently. So the first observation has nothing to do with the second and so on. I choose a sample at random and in an independent way. So the variance of this linear combination is simply the constant square times the variance of x1 plus the constant square times the variance of x2 and so on. So it is 1 over n squared, that's the constant square. 1 over n squared times sigma square, it's the variance of x1, plus 1 over n squared sigma square, variance of x2, plus and so on, plus 1 over xn, which is the constant square, 1 over n squared, 1 over n squared times sigma square. So again, we can take 1 over n squared as common, and then open bracket, we have sigma square plus and so on plus sigma square. How many terms do we have? Again, it is n terms. So this expression is equivalent to n sigma squared divided by n squared. So this n will cancel with one of the n's that we have in the denominator, and the whole expression is equivalent to sigma squared divided by n. It is nothing new. We know from chapter 5 that if x1, x2 until xn are random variables and we define their average, x1 plus x2 plus and so on until plus xn divided by n, the variance of this expression is equal to sigma square over n. Now, let me summarize. Let me put things together. What we covered so far is this blue part of our ideas here. So if we have a population, that has a normal distribution, and then we choose a sample at random from this population, and we calculate the average of this sample itself. Let's call this average x bar. What did we know so far? That x bar has a normal distribution. Actually, that's nothing new. All this is from chapter 5. X bar has a normal distribution with mean mu and with variance sigma square over n. Now, what is the central limit theorem then? This is what will come in the next slide. Imagine that population now is not normal anymore. So here, this assumption that x or our population has a normal distribution is not valid anymore. So this population has a distribution which is not normal, or even its distribution is not known. So we have a population of random values, Its distribution is not known, so it might not be normal. What can we say here? How can we extend what we have done for the normal distribution? Basically, that's the power of this theorem, because the central limit theorem tells you that if we choose a sample from the population, given that this sample has a large enough size, so the size of this sample is large, and I'll basically comment on that in the next slide. The size of this sample is large, and then for that sample, we calculate the sample mean x bar, which is the average of our sample. What do we know about this sample mean x bar? It still has a normal distribution. It's an approximately normal distribution, really close to the normal distribution. So what is the power of this theorem? If we have a population and the population has a distribution which is not known. So imagine, let me choose another example. This is the population which contains all the waiting times, all customer waiting times at an airport check-in counter. Imagine that we have a check-in counter. Any customer who waits there will wait for a particular amount of time until the customer checks in. Obviously, that time would change from customer to customer. So let's say the waiting times are random. Imagine that I know they are random, but I don't know the distribution. So is it normal? Is it exponential or anything else? I don't know the distribution. Now, let's say I stand at this check-in counter and I choose a sample of size 50. So I observe 50 customers that I choose at random. So 50 randomly selected customers. And for each customer, I observe the waiting time. If I calculate the average of those 50, not the average of the entire population, the average of those 50 that I choose at random, we know that that average, x bar, the sample mean, has a normal distribution. Imagine the power of this. I know that x bar, the average of the randomly selected sample, has a normal distribution, even if the population is not normal, or even if the distribution of the population is not known. So let me proceed. Now, let me go back to the case in which the population had a normal distribution. That was nothing new. If I choose a sample at random and I calculate the sample mean has a normal distribution, and this is known from chapter 5. Now assume that the population is not normal. Now assume that the population I'm choosing the sample from is not normal. So I'm talking about GPAs. I know that the different GPAs of all students in the world are random. However, I don't know their distribution. So I don't know whether the population is normal or anything else. What can we say? And this is according to the central limit theorem. By the way, we just discussed the result of the central limit theorem with no proof. So the proof of the central limit theorem is involved, and it's beyond the scope of this course. Now, what we know, what the central limit theorem tells us, is that the sample mean x bar is still approximately normal if the sample has a large size. So in practice, if the sample has size 30 or more, so if our sample contains 30 or more observations. So if I'm talking about GPAs, the group of students that I choose at random is of size 30 or more. Or if I'm talking about people's heights, I choose 30 or more people as a sample. Or if I'm talking about the waiting time at a check-in counter, I select a group of customers at random that has a size of 30 or more. If the sample size is 30 or more, then the sample mean, the average of this sample, has an approximately normal distribution, very close to a normal distribution. Also, what we know also is that if the sample size goes to infinity, if the sample size, in theory, goes to infinity, if you have a really large sample, then X bar is exactly normal. So what is the bottom line here? The bottom line is that if we choose a large sample from a population, if we choose a large sample, and in practice large, it has been observed of size 30 or more, so at least a size of 30. The sample mean X bar of this population has a normal distribution with mean mu, which is the same as the population mean, and with standard deviation sigma over root n. Sigma is the population standard deviation, but it's divided over square root of n. Where is this coming from? It's coming from here. If the variance of the sample mean is sigma square over n, then the square root of this, the standard deviation of X bar, is sigma over the square root of n. Let's say this in compact notation. So what we know, as long as the sample is large and it's coming from a population which could be normal or not, even I don't care about the distribution of the population. As long as the sample is large, as long as our n is greater than or equal to 30, we know that the sample mean X bar, the average of our randomly selected sample, has a normal distribution with mean mu and standard deviation sigma over root n. Obviously, mu is the population mean and sigma is the population standard deviation. In other words, mu of our sample mean, mu X bar, is equal to mu, and this is the population mean. Sigma X bar is equal to sigma over root n, and this is the population standard deviation. Now let me show you the slide. What does this slide say? It says exactly what we have said in our previous notes, but we said it in full detail. So to summarize, if we say that x1, x2 until xn is a random sample, a sample that we choose at random from a population, and if that population has mean mu and variance sigma square, so this is the population mean and this is the population variance. If we choose a sample at random from this population, and then we calculate the sample mean X bar, the average, not for the population, no, the average of that selected sample. What we know is that X bar has a normal distribution with mean mu and with variance sigma square. In other words, if we standardize, so if we take X bar and we subtract mu and we divide by sigma over root n. Again, what was sigma over root n, by the way? Sigma over root n was the standard deviation of the sample mean. So sigma over root n is a standard deviation itself. However, sigma on its own is the standard deviation of the population, but sigma over root n is the standard deviation of the sample that we have chosen at random. So if we take X bar, the sample mean, the average of our sample that we have selected at random, we subtract mu and we divide by sigma over root n, we know that this fraction here has a standard normal distribution, and this applies if n goes to infinity. So theoretically speaking, if our sample has an infinite size, then X bar is exactly normal. However, in practice, if the size is large enough, it does not have to be infinity, 30 is enough. If our sample has size 30 or more, then X bar has a normal distribution. In other words, X bar minus its mean divided by its standard deviation has a standard normal distribution. Let me just show an illustration. This is an experiment basically that shows this idea. So this is a really nice experiment that shows the idea of the standard of the central limit theorem. So we will talk about that experiment, and then we will see an example that will summarize it all, that will make it really easy for you, inshallah. So let me go back to this illustration. You all remember the rolling the die example. We have a die. A fair die has numbers 1, 2, 3, 4, 5, 6. And then if we roll the die, What is the probability of getting a 1 or a 2 or a 3 or a 4 or a 5 or a 6? All these outcomes have the same probability. That's why you see the same probabilities for each one of these outcomes. Now imagine that we roll 2 dice and then we observe the average of the 2 outcomes, not the 2 outcomes themselves, but the average of the 2 outcomes. What are the possible values of the 2 outcomes average? It's also between 1 and 6, but the probabilities are not exactly the same. Simply speaking, what's the probability that the average of both dice is 1? When is the average of both dice equals to 1? The average of both dice is equal to 1 if both give us a 1. If you roll these dice and then you get 1, in that case, the average is exactly equal to 1. If you roll both dice and both of them give you a 6, then the average is equal to 6. Obviously, getting an average of 1 or getting an average of 6 has a lower probability because it has only one possibility, getting 2 1s or getting 2 6s. However, how can you get an average of 3.5? For example, we have many ways that gives us an average of 3.5. So if one of them is a 1 and the other one is a 6, the average is 3.5. If one of them is a 2 and the other one is a 5, the average is 3.5, and so on. So that's why if you focus on the average of these 2 dice, the respective probabilities are not uniform anymore. We have a smaller probabilities for the 1 and the 6 and higher probabilities in the middle. Now, if we make it 3 dice, the distribution of the probabilities of the averages are getting closer to a normal distribution. With 5 dice, the probabilities of the average values are getting closer to a normal distribution. With 10 dice, imagine that you're throwing 10 dice at the same time, and then you calculate the average of the outcomes that you get. When is the average equal to 1 exactly? If all 10 dice give you a 10, how likely is that? What is the probability for this? Very small. When is the average equal to 6 exactly? If exactly all 10 outcomes are 6, and this has a very small probability, but the probabilities of the other values of the possible averages have other values. Specifically in the middle, we have the largest probability because we have so many possibilities to get those values as an average. So as you notice, the average has a probability distribution. The average outcome of 10 dice has a probability distribution that is coming really close to a normal distribution. Imagine 30 dice, it's perhaps exactly normal. And this is what we meant by the central limit theorem. Now let's talk about an example so that we cut it short. In this example, we say the following. An electronics company manufactures resistors. So we have a company that manufactures resistors. The mean resistance is 100 ohms. So obviously, we wanted that the resistance value of each resistor to be 100. However, because of the errors, we get different values. So the actual resistance value is a random variable with mean 100 ohms and standard deviation 10 ohms. So this is given to us. Now, is this regarding to the entire population or regarding a sample? No, this is regarding the entire population. Nobody talked about any sample in this first sentence. We're just saying that resistors in general, regarding any resistance that comes out of this manufacturer, the average is 100 ohms and the standard deviation is 10 ohms. It is given to us also that the distribution of resistances is normal. So resistor values that come out of this company have a normal distribution. Now, what is the question? Find the probability that a random sample of 25 resistors will have an average resistance of 95 ohms. Now, we have to be careful here. Is the question here, find the probability that X is less than 95? If we think of X as any resistance value in the population, is the question, find the probability that X is less than 95? No, it's not the probability that X is less than 95. The question here is about an actual sample of size 25. So imagine that you go to this company, you close your eyes, and then from the production, you choose 25 resistors at random. You take those 25 resistors, you put them in a box. That's your random sample. Now the question is, what is the probability that the average of that sample is less than 95? Let me proceed with my own notes here. So if we think of X as the population of resistors, so the population that contains all the resistors. What was given in the question? What was given that mu x is equal to 100. The average for x itself, the mean of the population, is equal to 100. And the standard deviation of the population, so sigma x, is equal to 10. This was given from the beginning, 100 and 10, mu and sigma. In addition to this, it's given to us that x, so the population of resistors, the resistance value x in general has a normal distribution. So to put it in short form, we say that x, the resistance values in general, belong to a normal distribution with mean 100 and with standard deviation 10. Mu is 100 and sigma is equal to 10. If our question was about resistors in general, so if that question was in chapter 4, we could have said, what's the probability that this x is less than 95? In that case, we standardize, so we subtract 100 and we divide by 10. But that's not the question here. Since this question is in chapter 7, we are talking about a sample. As I mentioned in the previous slide, let's say the question itself says that from that population of resistors, we take a sample of 25 resistors at random. So you go to this company, you close your eyes, and from the production, you choose or you select 25 resistors at random, you put them in a box. Of course, you can measure each one of these resistances. However, you also have so many samples that you could have chosen at random. So if I go and choose, maybe I have another 25 resistors. If someone else goes, maybe they have another 25 resistors, and so on. So the question is the following. What is the probability? What is the probability that the average of the sample that was chosen at random is less than 25? How can we solve this question? We can solve this question by doing the following. First of all, because the population of resistors was normal, then we know that the sample mean of any sample is also normal. But normal with what mean and what standard deviation? So we have to calculate mu x bar and sigma x bar by borrowing the results of chapter 5 that we have reviewed here as well. Mu x bar is equal to mu is equal to 100. So if we take a sample from a population, the average of the sample has a mu equal to the same as the population mu, which is 100. And this is what we have seen here. Let me recall, this is what we have seen here. The expected value of x bar is equal to mu, and the variance of x bar is equal to sigma square over n. In other words, the standard deviation of x bar, this is sigma x bar, is equal to sigma over root n. And since our sample here in this question has a size of 25, so sigma x bar is equal to sigma over square root of 25. So it is 10 over 5, which is equal to 2. So how can we combine everything? How can we summarize everything? X bar, which is our average of the 25 resistors that have been chosen at random. X bar, which is the average of the 25 resistors chosen from the population at random. This X bar has a normal distribution with mean 100 and standard deviation 2. So this is mu x bar, which is the same as mu, and this is sigma x bar, which is the same as sigma over root n. So going back to the question here, if the question says, what is the probability that the average of your sample is less than 95? So mathematically, what's the probability that x bar is less than 95? Not x bar, the average of your sample. X bar is less than 95. Now, from this discussion, we know that x bar is normal. Now, so to get this probability, we need to standardize. So instead of x bar, we use z, and then we standardize. So 95, we subtract the mean, and we divide by the standard deviation. But don't forget, we subtract the mean of x bar, which is 100, and we divide by the standard deviation of x bar, which is 2. So we subtract mu x bar, and we divide by sigma x bar. So 95 minus 100 over 2. Using the calculator, this is minus 2.5. So to answer the question, what is the probability that the sample mean is less than 95? It's equivalent to the probability that the standard normal variable z is less than minus 2.5. So how do we solve that? From chapter 4, we just go to our standard normal tables and we look up minus 2.5, and that will be the answer itself because it's a probability to be less than. So from the table, that probability that we need is 0.006210. Now to recap, what is this probability exactly? That 0.006210. Is this the probability that any resistor in the company is less than 95 ohm? No, that's the probability that the average of your sample of size 25 has a value less than 95 ohms. Now I have a couple of comments, and please concentrate with me. The lecture is almost over, so concentrate with me for the coming 2 minutes. Is this result approximate or exact? If you understand this, it means that we understand the whole lecture. Is this result approximate or exact? Actually, this result is exact. There is no approximation here. Why? Because in that question, it was given to us that the population has a normal distribution. It was given to us that the population of resistors has a normal distribution. That means that if we take a sample of any size, the sample mean has also a normal distribution regardless of the size. So let me go back to this illustration here. If we have a population, as long as this population is normal, if we take a sample of any size, X bar has a normal distribution. So what would change? What would change in the question? How could we have solved it if this was not given? If I just take this out, the distribution of resistance is normal. It's not true. That's not given here. Can we still solve the question? The answer is yes. We could have solved the question, and the answer would have been exactly the same. However, we needed a size of the sample which is 30 or more. So with a size of 25, perhaps we are not sure that X bar is normal or close enough to normal. However, we cannot do anything about it, so it cannot be solved. However, if I remove this normal distribution and at the same time I make the size of the sample 30 or 36 or 49, any value greater than 30, in that case, I still say that the sample mean has a normal distribution. This number would be exactly the same, but this number would be different. So it would be 10 divided by the root of the new size of the sample. So if the size of the sample was 36, this would have been 10 divided by 6, and we have another value, 1 point something. But the idea of the solution would be exactly the same, but this number would be different. So let's summarize. When is the sample mean normal? When does the sample mean have a normal distribution? If the population it's coming from has a normal distribution, then the sample mean has a normal distribution, and this is exact. There is no approximation. However, if the population from which we take a sample has not a normal distribution, so its distribution is not normal, anything else, or if the distribution is unknown to us, then what we need is that the sample that we choose at random has a size of 30 or larger. So if the sample has a large enough size, going back to this picture, if the sample has a large enough size, then X bar still has a normal distribution. Bottom line, and to cut it short, could we have still solved the problem if it's not normal, if the population of resistors is not normal? Yes, and the solution idea would have been exactly the same. However, we needed n to be 30 or greater. This finishes this part. This finishes today's lecture, and we will continue with another idea next time.